Hey everybody, thanks for coming to the talk. Obviously, Armin gave me a fantastic plug in the keynote yesterday, so hopefully I'm going to keep you entertained for the next while. So I'm a industrial researcher at a startup. I think that is something of an oxymoron. Most startups don't have a research department. So how did I get to be here? For academics, Google Scholar is sort of the place to go. Rather than going to my GitHub repo, you should go check me out on Google Scholar to see my previous work. I had the privilege of being at Microsoft Research's Silicon Valley lab for a number of years, and this was during a really interesting period. MapReduce had just come out. I got to work on a series of projects under the Dryad umbrella. Dryad was kind of our response to MapReduce in a sense, but it was a very academically principled thing. We were really driven by the desire to harness distributed data flow, and we did a series of projects. The Quincy scheduler is very cool if you haven't seen that work, where we actually again used network flow optimization as a way to schedule the work on a cluster. Then we did a GPU accelerated version and stuff. We were lucky to have product impact. A lot of the Bing backend offline analysis runs on Dryad. The first version of the Connect motion tracking machine learning was trained using our cluster stuff because they had 25 million images with depth information to train decision trees. And also, the double win in research. We've also managed to sort of have impact on downstream projects. Some of the ideas were taken into Spark. The reason I'm at HashiCorp was that Arman, when researching Nomad, had looked at the Quincy scheduler, so that's how we connected. And TensorFlow is an interesting one, actually. 7 of my ex-colleagues who worked on these projects actually, when we were laid off, when Microsoft closed our lab, 7 of them went to work with Jeff Dean and helped to write TensorFlow. So, a very definite direct transmission of some of the ideas. Prior to that, I've also done research at Samsung, but I've walked a mile in your shoes. I helped to build the iTunes Store. I was the first engineer to work on video. I built out and then had a team who built out the whole video ingestion pipeline. So I've walked a mile in your shoes while stabbing myself in the eyes with forks, because we did DevOps without the tools, and nobody even knew we were doing DevOps. We were just filing a lot of tickets all the time, and it was a crazy time. The kind of theme to my work has always been scalable distributed systems of one flavor or another, going back to J2EE and this thing called Corba, which luckily most of you never had to deal with. It's a long time ago, but it actually laid down a lot of the ideas for these remote, service-oriented architecture middleware paradigm. Okay, but today we should talk about something concrete, real world. This is the scenario that Arman actually mentioned in the keynote, and it's a really good one to explain a problem that a number of our users started to encounter when using Consul. And the investigation that we undertook and how we actually resolved this problem. So many people will have a cluster of some kind, whether this is bare metal, on-prem, virtualized in the cloud is irrelevant, but you have a bunch of machines and you've got some ingress and egress. Maybe you structure things such that you have some edge nodes, and then you have the interior where you're spinning up different services and so forth. And you're here, so maybe you're using Consul or Surf to help you do the discovery and availability for this. And of course, so now I'm showing the green nodes are the ones that Consul is declaring as healthy. The red ones are the ones that are currently failed. And what if something happened like a DDoS attack? And this is again, the real world motivating example. We had some users using this stuff at scale who were getting hammered hard from the internet. And yeah, the edge nodes get overwhelmed, and so people have to scramble, and you're going to have to do all that good stuff to try and change the traffic and keep the DDoS stuff out. It's going to impact the rate at which your real traffic, your users can progress. But hopefully it will be isolated to the edge. I mean, it's the edge machines that are getting hammered, so those are the machines that are going to have to be fixed up. What we saw was node flapping. What the users saw and what they came to us for help about was seeing node flapping in the interior of their cluster. So What do I mean by node flapping? So there are healthy nodes that are being marked as failed by Consul, but then soon after that, they're being marked as healthy again. And then if you go in and do an investigation and you look at the logs, you'll see that by all the other metrics you've got, that node was never actually unhealthy. And there are other healthy nodes via Consul who are believing that this node was failed. So what the hey? This is not a good situation. Break glass, call HashiCorp. So to explain what was going wrong here, I'm going to have to talk about the swim protocol, because it's the swim protocol underlying this, and that's where the problem turned out to be. I'm going to give you a little bit of context of where swim comes into relation to the HashiCorp stack. I'm going to walk you through the problem, Lifeguard as a feature, and then interestingly, by going and doing the paper after we released the feature, we are actually able to make the feature better. So I'll talk to you about how the process of writing the paper informed the actual the stuff that you guys get to use. So you're certainly familiar with Consul. Less people are familiar with Surf. Surf you can think of as a subset. Consul is built on top of Surf and provides a subset of the features. We had an awesome talk yesterday from Fastly talking about how they use Surf in their content distribution network. So you don't always have to have all the features. Nomad also makes use of Surf for its own failure detection. So Consul offers health checks, and that's one of the Consul level features is user-defined health checks. But there's also this built-in health check, and it turns out the built-in health checks are actually coming from Surf. It's coming from underneath in the stack. And what's really nice about the built-in health check is at the node level, it's ANDed together. You have your service level and your own node level health checks. We have this additional provided health check. If our health check fails, it's an AND rule, because we're telling you that this node is bad. So it doesn't matter what your applications think is going on top. So it's a sort of belt and suspenders, extra level of protection that you get from Surf being surfaced into Consul. Now, because we're baking this thing in and because we're ANDing it, so this is something that's going to take your service offline if we're wrong. We need this thing to be robust. It's got to be scalable. It can't have too much impact in terms of network load and load on the hosts. It can't be a many-to-all or even many-to-many. To scale to 10,000, 100,000 node scale, which we have people deploying on single clusters of 100,000 machines. And to do that, this thing has to scale very nicely. And also, it's the watchdog, so it itself has to be fault tolerant. We can't take part of your system offline because this system is not robust. So we have to have a fully distributed failure detector. That's how we can give those guarantees. And it turned out that looking around, there's this awesome piece of work, Swim, and it has these properties of a low network load. It propagates updates quickly, and it converges fast. It can work because of this at massive scale. And it turns out we have a repo called memberlist. So memberlist is where our Swim implementation lives, and this is underneath of Surf, and then in turn Consul depends on Surf. So transitively, they're both using memberlist under the hood. Okay, so we're going to dive into Swim now. So in 2002, at a nice academic conference, work out of Cornell, Werner Vogels, the CTO of AWS, was actually an academic at Cornell at this time. He wasn't involved in this particular piece of work, but very strong school for distributed systems, still is, and pioneered a lot of stuff back in the 90s and zeros. And the Swim protocol has two parts. There's this failure detector. And you'll see in the paper and in my slides, we talk about probes being sent. And then once a failure is detected, we need to disseminate that information to everybody in the cluster. So the second phase is the dissemination mechanism. Both of these phases, the way that it can be so scalable is that they're peer-to-peer, they're fully distributed, which they don't send, the number of messages is independent of the size of your cluster. They also don't offer consistency guarantees, but they do converge fast. And they make use of randomization, and we'll see that as well. So the failure detector, the front end of Swim, it works in rounds. And in each round, each member will pick another member at random, and they will send a probe message to say, this is the health check. Are you alive? And this is all asynchronous. There's no synchronization. Each node is basically like on a 1-second timer. Every second it picks somebody and probes them. Now there's this expectation. This is just stats talk. On average, you would expect everybody to be pinged by somebody each round. It's lumpy. It doesn't actually work out exactly like that. To try and smooth it, each node actually round robins through all the other nodes that it's aware of. But to stop that being correlated, when it discovers a new node, the new node is inserted randomly in its list. So everyone's got a mixed up, different sort of randomized list, but they each cycle through their own list of everybody they know about once before they go back. So that tries to, it actually does give an upper bound on how long it takes before you will be contacted. So within the probing, first there's a direct probe. This is a UDP message, and everything's going to be UDP from here on out. Node A decides to ping node D, so it sends this probe message. And if things are working, D hears the message, it sends back an ACK. And that's good, so success. We know that we did not detect a failure. A can assert that D is alive right now. If it didn't get the ACK back, we go to indirect probe. And this is a nice little thing that, there could be a problem with the routing, the direct communication between A and D. So A enlists, again, picking at random, 2 more of its peers. In fact, I think we go with 3. In the paper and in our implementation, it's 3, but it's simpler to show with 2. You pick some peers and you ask them indirectly, you say, hey, would you ping D on my behalf? And they go ahead and do that. And if they hear back, then they send the ACK back. So there's, two ways to win. Or actually, 5 ways to win or something, because we're doing this 3-way fan out. Now, if this doesn't work, if we neither directly or indirectly have confirmed that node D is alive, then we need to start saying, there's a problem here. And this is where the dissemination mechanism comes in. And so we only propagate, rather than doing this round-based, always sending these messages, only when there is an event, a state update, we're declaring that somebody is dead or alive. Now we need to propagate this state change message. So in this case, A had not heard back about D, directly or indirectly. So it now starts to send out this message saying, hey, I think D's dead. And this is an epidemic. It's a gossip protocol, but it's epidemic. It spreads like wildfire. People have done the math on all of this, and it will rip through the network very quickly. There are incarnation numbers associated with these messages because you've got it's fully decentralized. There's no central authority here. So you have these competing messages. Hey, I heard he's dead. I heard he's alive. Well, you have an incarnation number to broker say who wins in that situation. And then the nice thing they did is they said, you know what? Everybody's pinging somebody once per round. Why don't we just piggyback these update messages on those probe messages? So actually, in the sort of base case, there'll be no additional message load. You've got an MTU, like 1,500 bytes of UDP, and it's a very small packet that we had, and we can piggyback 5 or even maybe 7 or something of these messages on the back of the probe message. And yeah, it works really nicely. We actually have a little simulator. It's just a JavaScript thing, but it executes the math, and you can drag sliders around. If you go to the surf docs page, and you can see that here we're talking about 10,000 nodes, and we're looking at the failure rate, and even though we have some packet loss, and we've constrained the bandwidth, and yet within 2 seconds everybody gets the update. And if you tweak these parameters, you can keep the update rate acceptable even at like 100,000 node scale. However, the authors of the paper, even before they got to finishing and publishing their paper, they had observed that if a node was running slow, it could mess this whole thing up because I'm sending a probe and I'm expecting an ACK, and if somewhere along the way, the message doesn't get to somebody in a timely manner, I could quickly declare somebody is dead and he's not dead. And their solution was to basically add an extra state and an extra set of state transitions. So they talk about the suspicion mechanism and going to a suspected state. And pretty much, so the interesting thing here is while this is a way to make the fault detector more robust, it is actually implemented in the update dissemination phase. So it's an interesting kind of hybrid, or you could think of it as a bridge between the two parts of the protocol. So in this case, A did not hear back about D. Instead of going straight to declaring D is dead, A now says, I suspect that D is dead. And because we're using the dissemination mechanism, which has this epidemic quality to it, any healthy nodes are going to hear and forward this message quickly. So if D actually is alive, D is going to hear the message that, hey, A is saying you're dead. And this is an opportunity for D to come back and say, you know what, I'm not dead, I'm alive. And it actually increments the incarnation number, and this is how we get the assertion that, the most fresh information in the system now is D confirming that it is alive. So that's the suspicion mechanism. They are trading higher latency in detection for a lower false positive rate. And it's all good, and in the paper they show the reduction, the effect of this. They only tested on 55 nodes on a 100 megabit network. This is what people had even in a Ivy League school in 2002. The cloud scale wasn't there yet. Werner Vogels was still doing academic stuff. So, it's not a surprise that this stuff didn't scale to 100,000 node or even, 1,000 node scale. They just didn't have an opportunity to test it at that scale. So we go back to this problem. And great, they've added this suspicion mechanism, and it's precisely the kind of thing that this was designed to solve. So why do we have this flapping problem when they've gone to the bother of making the protocol more robust to slow processing? So what's going on here? So Lifeguard was implemented as a feature first, and then we came back and did this sort of academic investigation of it. So we're going to talk about actually what went into code first. Looking at the logs, working with the users, this was the basic issue. Even though they've added the suspicion mechanism, D has this opportunity to refute the fact that it's dead. But if A, as the node that had the suspicion, that started to gossip this suspicion, if A is running slow, that alive message could even get back to node A, but it could be sat in a queue of messages somewhere in the network stack, or even as a Go routine queued up. It hasn't got it to run on a thread yet. And as a result, the timeout passes. A goes ahead and says, you know what, you had your chance. You didn't tell me that you're alive. You're dead. And that's the fundamental issue here, is that even though they observed that slow-running nodes could cause this problem, and they put a mechanism in place to address it, the mechanism they put in place is still vulnerable to slow nodes. So this was the problem we were faced with. And the second observation sort of showed the way out of this problem. There's a lot of messages flying around, and you initiate a bunch of messages, and when you initiate a message, you often expect a response. If you don't get that response, the absence of that response is actually a piece of information. Sometimes, no news is news. So this is the key insight of Lifeguard, is that we can, knowing what messages we would expect, if we don't receive those messages, we can start to use that information as a signal and relax the timeouts. We could be the problem, the local node. And this plays out in 3 places. So L1, L2, L3, these are like 3 components of Lifeguard. And it starts closer to home, or at the beginning of the algorithm. First, we dynamically adjust the fault detector timeouts. This is on the probes and expecting back the ACKs. And then the next phase, if you get to suspecting somebody, we can, again, use information to decide whether we should wait longer to hear back, give the suspicion mechanism longer to work. And then finally, slightly differently, the node that's suspected has to receive the message in a timely manner, and there's actually a little tweak that we do there. And I'm going to talk you through these briefly. So what we call self-awareness, the probe intervals, again, you're sending probes and you're expecting ACKs. And if you don't receive an ACK, whether it's for a direct or an indirect probe, you can, we should start with by default, we start with the timeouts on these probes low. And if we don't, especially in a correlated manner, because we're probing one other person once per second, and if after a few seconds we haven't heard back from any of these guys, we have to weigh the probability that they all just failed versus that it's a local problem. And we don't, all we're doing is relaxing timeouts. And of course, it's fully distributed. So even if we say, oh, I'm going to give that guy longer, there are other people who are not running slow who are not going to adjust their timeouts. So this actually doesn't make us vulnerable as an overall system. We're pretty much saying if the local node is running slow, it's going to recuse itself of being an aggressive judge of other nodes. And there's actually two things we vary. So there's the probe timeout. If I send a probe, how long before I fire a timer saying I didn't get the ACK back, either progress to the indirect or to suspicion. And the other thing is the interval. I said that like once a second, the rounds are once per second, but we actually now allow you to slow down as well. If I'm an unreliable judge right now, let's just take myself, slow down. Let's not throw myself into the mix as often. So the way we change both of these is using, we have this notion of a node self-awareness counter. And the higher the value, the worse we think we're doing, potentially. And so it's just a multiplier. And we add 1 to make sure it's never 0. We don't want to have 0 timeouts here. And it's a heuristic. We have tuned these things a little bit after experimentation, but it worked surprisingly well out of the gate. Basically, every time you don't hear back a message that you expected. Also, if you have to refute a suspicion about yourself, that's a slightly different thing, but basically, that's another sign that, people are suspecting you. You could be running slowly. So those three things add to the counter, but if you hear back an ACK, we decrement the counter. And we make it a saturating counter. We put a cap on this thing, and in the case the default configuration value is 8, to say, we're going to slow down by a factor of a maximum of 8. Interestingly, we also counted NACs. Now, the NAC is not part of the SWIM protocol. But since we're now interested in discovering information from absence of messages, it seemed like a good idea to add these messages. Now we have one more signal. Without the NAC, if A doesn't hear back from an indirect ping of D, it doesn't know whether the problem was with D or with B and C, or with itself. And now the NAC can be used to differentiate that. We know that, hey, I can talk to B and C. That's probably not me. That's probably D. But if I don't hear the NACs back, it's probably me. So moving down the pipeline, if slowing down on the probes hasn't helped, we get into the suspicion phase. And it's the same game. It's actually played in reverse. We start with a high suspicion timeout. Once we suspect somebody, and then we lower the timeout if we hear back these independent suspicions. Because basically, if D really is unhealthy, we shouldn't be the only one who should have failed probes, who should go on to having a suspicion. There should be other suspicions floating around in the network, and we can use that as a signal. If I'm not hearing anybody else's suspicion, maybe I'm isolated, I'm running slow. So this is what it looks like. There's a sort of step function. When you start with a local suspicion, we start with a maximum suspicion timeout, and each time you hear back, you hear of somebody else's suspicion, you lower the suspicion timeout, and then you get down to the min. And out of the gate, our min was the old pre-Lifeguard suspicion timeout, but we'll come back to tuning that min value towards the end. And here's the math of it. So basically, we count how many suspicion messages, independent suspicion messages about that node that I suspect. How many independent messages have I received from other nodes? Let's see. And then we have some value k we've picked. How many independent suspicions would I like to hear before I decide, yeah, I'm really well connected. I'm just going to go to my min and time you out quicker. And it's a little equation there, but basically we're only going to ever have a timeout between the min and the max. And then we are using log value because we want to be sort of biased. If I hear back one message, one suspicion from somebody else, I am at least connected to the network. That kind of is the biggest piece of information. So we drop the timeout the most, in the first step, and then it's sort of logarithmic. It decays. Additional information gives us less surety. And then again, we add 1 to make sure that because the log of 0 is going to be infinite, and that's not what we want. So it's actually pretty simple. It gives us that step function in the graph. And the third thing, the buddy system, as I was saying, we need. It's interesting. The SWIM paper suggests that anybody can refute. That node B can say, hey, I had a successful probe with D, so I'm going to tell you that D is alive. The issue is, when you come to implement this thing, given that it's fully distributed, asynchronous system, only D really can increment its incarnation number. And that's the definitive piece of information. You're not going to be guaranteed to win this argument unless you get D to increment its incarnation number. So it's really important that the node under suspicion gets the message and sends back a refutes with an alive message. And this is a simple tweak. Basically, there's this piggybacking, and we just give priority. We say, hey, if you're going to probe a guy and you happen to know there's a suspicion about him, let him know. Be a buddy. Just let him know that he's got a target on his back. It's like, this is how we play this game. This is the code of conduct. And it's interesting. It's a subtle thing. It makes a difference. And we shipped a year ago, actually. And it made an immediate difference to people had already tried this out, some of the people who had a real pain point with this. And it wasn't just that DDoS. Any time where you have something that is sort of internally DOSing your system with spinning out of control on CPU, or if you're working on an instance that's CPU limited, in a virtualization or something like that, you could get into a situation where Consul agents started to behave erratically like this. And so we got the work out there, and then we said, hey, wouldn't it be great to actually go and write a paper about this and to share our experiences? So that's how we got into doing Lifeguard the paper. And it's out there. As Jack mentioned, this is a preprint. So if I was talking to you 4 years ago as an academic computer scientist, I would say the paper is under submission to Conference X, or maybe I wouldn't even tell you which conference. You wouldn't get to see the paper until it was published in a peer-reviewed conference setting. But physicists have always shared their work early because it's real science and they need people to reproduce their results before it can get, just saying, before it can be accepted to a journal. And the last few years, it started with the deep learning. The deep learning community, that work is moving so fast that the time lag of waiting 9 months, it's under submission, the conferences, that latency was killing them. So the deep learning people started publishing, pre-printing their stuff on, so Archive, it's out of Cornell, it was built for physicists, but everybody's using it now. And it's caught on like wildfire. So a lot of people are pre-printing. We're now going to submit this to an academic conference. This is not the final version. We need to add some more, positioning with relation to previous work, related work. We need to add some more experiments. So this would not get it accepted to a conference in the state it's in. It's kind of more white paper at the moment, but we will be submitting it to a conference. But we wanted people to be able to understand what we've done and give us feedback earlier. So that's why we pre-printed, and we will take it down ultimately if it gets accepted to a conference, because they'll then own the copyright. The methodology. So we have two different environments. To repro the problems that users were telling us, we have a sort of soak test. We can run it on AWS or Azure. You pick one of those micro instances that has CPU budgeting, and we use Packer and Terraform. We spin up a cluster. We have some little workloads that churn CPU, and if you run those long enough on a micro instance, you watch on CloudWatch, and the CPU budget gets used up, and the node gets starved. And this is a good sort of reproduction of a real problem as witnessed in a public cloud environment. For the results that are in the paper, we wanted to do a real sort of data cube, explore the space of all these different parameters. And the sort of simplification is that we use a single Ubuntu VM. Because Consul's written in Go, and Go is awesome, we can spin up 128 instances on a 16-core machine. We then induce the pathology in a very controlled manner. We go down into the net.go library, and we can say, okay, stop sending and receiving messages for this interval of time. And we can control very precisely to sub-millisecond accuracy, when you start and stop having this anomalous behavior. So it's allowed us to sort of do the data cube. I burned at least $80,000 of time in Azure to do this, and thank you to Microsoft for giving us the credit to do that. So we were able to do a very principled investigation, varying how many concurrent anomalies, the duration of each anomaly, the interval between anomalies. So a very big data cube to investigate. How do you evaluate this? Well, the swim paper actually had the right metrics. The thing we're interested here is the failure detection false positive rate. The flapping is somebody being falsely accused. So that's the thing that Lifeguard sets out to reduce. The problem is, what are we doing to latencies? There's the first detection, when one other node called it and said, yep, suspicion has passed, you're dead. So that's the time till somebody detects it, and then how long from there to propagate that through the epidemic protocol. And then message load, how many more messages are going to be flying around as a result of this? So the headline thing that Armin showed, now here, I've broken it out. There's those three components: self-awareness, Dogpile, and Buddy. Just for interest, I'm showing you, that each of those has a contribution to make. On the left, though, we have without Lifeguard, and that's normalized. That's 100% of the error rate that we saw. And this is across all the experiments. And we do a whole bunch of crazy experiments, real torture testing of these clusters. And on the right is full Lifeguard. So if we compose all those three features in the middle, it's really gratifying. We were able to drive down the false positive rate by more than 98%. And also, I'm showing you the difference between the overall false positives. This is, these unhealthy nodes, not surprisingly, are accusing people left and right. What's really disturbing is when you have a completely healthy node, but because it's surrounded by enough bad actors, it's receiving these gossip messages, and it's joining in and saying, yeah, I think that guy's dead as well. Everyone's telling me this guy's dead. He's dead. Those are the ones you really unhappy about, because those are the nodes that are in service, and they're going to make decisions about failing over and rebalancing replicas and stuff. So it's really important to drive those down. And it's interesting to see the contribution, the relative contribution of the different components, and there's more about this in the paper. Latency, well, we do increase latency, but the nice thing is, and again, this is over looking at really pathological. At the extreme end of our tests, 1/4 of the cluster is just hawked. It's horrible, and even in those scenarios, the median first detection and full dissemination rates barely rise, 2%. There's a long tail, and the tail gets longer. But Swim is a randomized protocol. I have some good friends over at VMware Research who don't like Swim for this reason, and we're actually working with them to see if there are some other sort of ring-based, and there are some other alternatives that are more lightweight in terms of messaging and more predictable. So we are looking at that. We are actively evaluating whether we could slide in something next to Swim to begin with, if it is lightweight, and then ultimately even maybe sunset Swim, but not anytime soon, because it's super robust. And this is the worst case. Even when we're hammering the cluster and a quarter of the cluster is sick, the long tail only got longer by 16%. So and there's an upper bound on all of this. It's not like somebody's going to go undiscovered forever. Now, network load. There's actually two components to this: how many messages to be sent and how many bytes. Here, I'm breaking it out. The graph is showing you how many concurrent anomalies. As I said, things get kind of wild as you approach 1/4 of your cluster in a perpetual state of disarray. These are not dead nodes. These are nodes that are somewhat alive enough to be causing pandemonium in the network. They're spraying out all these accusations that are false because they're failing on their timeouts. So L0 is Lifeguard switched off, and that's the baseline, so we've normalized here. That's why it's a red bar at 100. The green bar is full Lifeguard. The other three are the different components. And again, it's really interesting to see the contribution of different components. The Dogpile, the suspicion mechanism, L2 is the one that actually really hikes up the number of messages sent. But again, on average, it's a 12% increase in messages. And actually, at the lower end, it can be a lot lower. It's like a 3% when there's only a handful of errors at any given time. And these are the pathological errors, not just somebody failed. If somebody fails cleanly, it doesn't ramp up the messages sent. What's really interesting is the bytes sent, because of all this piggybacking and because of the different stages of Lifeguard preempting this sort of cascading effect. What's really cool, if you look at the green line, is that while the maximum increase in the total bytes sent is 12%, if you look down at the left-hand end of the graph, when there are like 4 or 8 concurrent bad nodes, it's actually an overall reduction in the number of bytes sent, which is kind of interesting. So that we've headed it off at the pass by stopping the cascading effect. We've actually managed to reduce the total bytes sent, and this is the piggyback messages. The previous messages, these are discrete messages. These are not the individual messages that are piggybacked together. And this gives you an indication that there's actually less messages flying around because we've managed to dampen down the effect. But there's a nice thing that by doing this investigation, as we went in and ran these experiments and really deepened our understanding of why Lifeguard was working, the intuition and the initial heuristics were validated. But there's a thing that we observed. If you go back to the suspicion timeout stuff, the Dogpile, we've got this min and this max. And we started out by saying, well, we'll fall back. We'll start off more conservative, but we'll fall back. Min will be just back the way we were before Lifeguard. And what we realized was that now that we can discern bad actors and effectively filter them out of the active system, anybody who's healthy, why should they wait the same minimum timeout as before? We can lower the min timeout to be below the timeout that we previously had without Lifeguard, which means healthy nodes will detect failures faster. And that was the intuition. And so we ran the experiments. And now here I've got latency and the false positives at healthy, the ones we're really worried about. And again, the left-hand bar is the baseline. This is before we had Lifeguard, and then everything's normalized as a percentage. Alpha equals 5. So alpha is the multiplier. It's basically saying how many times the probe interval. If we're probing once a second, how many times do we wait the probe interval? Do we wait at a minimum for us when we're in the suspicion phase? So it's all based on if you increase the probe interval from 1 to 2 seconds, everything there's a knock-on effect with the math. But just by tweaking alpha, by lowering alpha, we've discovered that we basically have a knob here, which we can expose to the users, and you can make a choice. Alpha 5, we're biased. We've ever so slightly increased the median latency, but we've really knocked down the false positive rate. We're 98% reduction in false positives. But you can turn the knob if you lower that min threshold a little bit. Over a 15% reduction in the median latency for real detection of real errors, but still less than 5%. We've still managed a 95% reduction in the false positives. So we now have a tunable knob, and you can basically choose. In all cases, you're getting a reduction in the false positive rate, but you can now choose to trade some of that reduction for lower latencies in the healthy case. And that just is a really nice discovery. And we wouldn't have made that discovery if we hadn't taken the time to go and do this principled analysis. So how do you use this? Mostly just enjoy it, because we've done this investigation both in this sort of contrived setup and at the 400 node. The conference version of the paper will have the numbers at scale from the 400 node real virtualized environment. So there's really nothing for you to do. We went ahead and we changed the parameters. So you get about a 15 to 20% reduction in the mean latency for detection, and you get a dramatic drop in the false positive rate. If you needed to tweak it, the parameters are down there in the code. You can also monitor this. We've added a flap metric. So you can now go and see if nodes are being declared dead, and they're coming back I think it's somewhere in there, it's a configurable parameter, but if the node comes back to being healthy way faster than you could have cycled a node, it's flapping. So we have that metric in there, and you can use that metric to verify how well this is working for you. And if you still see a lot of flaps, or if it rises suddenly, then you're going to start. That's going to be a pointer to you to now go look at CPU utilization, go look at your Consul logs, and see if you're having this pathology. And then ideally, of course, remove that CPU hog. But if necessary, you could go in and tweak these parameters. And we are going to, once the paper is accepted somewhere, we will open this repo where all the work has been done. So you're going to be able to run this stuff yourself and look at the experiments and how we've done all the stats and everything, because we're committed to open research. And with that, I thank you very much.